Hello students, I am Vishwanath. Welcome to my YouTube channel. Today I am going to discuss about the force on a current carrying on conductor placed in a uniform magnetic field. In the previous video I already discussed about Lorentz force, that is force on a charge due to a uniform magnetic field. Today I am going to discuss about the force on a current carrying conductor when it is placed in a uniform magnetic field. Next, Fleming's left hand rule. Next, Barlow's wheel. Okay. First, let the a current carrying conductor having length small l placed in a uniform magnetic field. The uniform magnetic field is denoted by capital B vector. The capital B vector denotes the strength of the uniform magnetic field. Okay. The theta is the angle between the B vector and the axis of the wire. Let charge flows through the wire along the axis of this wire. Now the angle between the velocity of the charge and the magnetic field is also theta. V be the velocity of the charge. Now let us consider very small portion or element of the wire having length dl. In this wire, the small amount of charge dq passes through the wire along the axis of this wire having velocity v. This amount of charge, that is small q amount dq, small dq amount of charge experiences a force df due to this magnetic field. Therefore, we can write from Lorentz force or Lorentz formula that df is equal to dq into v vector cross b vector. Okay, and you know that v vector, that is velocity vector, is equal to dl vector with derivative of dt, that is dl dt cross b vector. And we can also write that df is equal to dq dt into dl cross b. Here dq dt denotes the current passing through the wire. It is denoted by I. That's why we can write that df is equal to I into dl cross b. Okay. For the whole wire, that is for the wire having length L, we can write the force F vector is equal to I into L vector cross B vector. Okay, this is the expression of force acts on the current carrying conductor, straight current carrying conductor placed in a magnetic field, uniform magnetic field. We can also determine the direction of this force by Fleming's left hand rule. Here the index denotes the direction of the magnetic field. The first finger denotes the direction of the current, and the thumb denotes the direction of the force when these three fingers are placed mutually perpendicular direction. Okay, therefore when the force, the current flows through the middle finger and the magnetic field acts normal to the current or normal to the axis of the wire, then the force on the wire is normal to the plane of the board or plane of the paper. This is known as Fleming's left hand rule, which is also known as the rotation of motors rules, or which is also known as the rotation of Barlow's wheel. Okay. Now the force between two infinitely long parallel current carrying conductor. That is, when two current carrying conductors, they are infinitely long, are placed parallel to each other, then they either attract or repel each other. Now I'm going to discuss about the magnitude of this force and nature of this force. Okay, here first wire carries current I1 and second wire carries current I2. R be the distance between them. Small r be the distance between them. Okay. Now the first wire generates the magnetic field B on the second wire. Therefore, we can write that B is equal to mu 0 by 4 pi 2 I1 by R. Now the force experienced by the second wire per unit length is F is equal to B into I2. Here L is equal to 1. Now putting the value of B, we can write F is equal to mu 0 by 4 pi 2 I1 I2 by R. This is the expression of the force acts per unit length of the either wire. When two currents are flowing in same direction, in this case or in this case, when the two currents flowing in the same direction or flowing in a same point at a same towards the same point, flowing towards the same point, then these two wires attract each other. That is, the force is attraction in nature. But when the one current passes towards a point and another current moves away from a point, then they repel each other. That is, when the direction of the currents are opposite to each other, then they repel each other. Then these two wires repel each other. This is the nature of the force between the two wires. This is a simple diagram of Barlow's wheel. This is a wheel which can be rotated with respect to the point O. Okay, this can be rotated with respect to the point O. This Barlow wheel is placed by a rod, and this rod, metal rod, this is a metal rod, and this metal rod is connected with a battery, and a mercury ball is placed such that the teeth of the wheel every time touch the mercury, and another wire is connected to the one point of the or one terminal of the battery to the mercury. A horseshoe magnet is placed such that the ball of the mercury is inside the horseshoe magnet. When current passing through this wheel, then this wheel rotates according to Fleming's left hand rule. Here the horseshoe magnet creates the magnetic field. Here this is north pole and this is south pole. Okay, and the rotation of the wheel is in this way. Here this is the direction of the current. Here this is the direction of the current, and therefore the wheel rotates in anti-clockwise direction. Okay, in this instrument we can convert the electric energy into mechanical energy. That's why it is also known as motor, or the principle. This Barlow's wheel rotates along the principle of the motor. You can increase the rotational frequency of the Barlow's wheel by increasing the current or increasing the magnetic field. Okay. Today I'm going to complete my discussion for here. Thank you for watching my video. Have a nice day.